Okay, so the next really important thing to understand about this category of functors from C to set is about monomorphisms. Okay, because this thing here is a topos, and as such, it has loads of great properties which allow us to manipulate monomorphisms. I mean, basically, a monomorphism into an object A can be, well, it is a sub-object of A, and it's a sort of generalization of the notion of a subset. And the structure of such things is very intuitive, really. For example, I've got a picture here of a sub-object X of A, or if you like, a sub-object M of A. I mean, there's this funny sort of usage of terminology. But I mean, in set to the power of C, we can basically think of. So, I mean, for example, I've got a picture here of a sub-object M of this object A, and you can see it's basically corresponding to a sort of subset of this of the loops and vertices present in this bouquet. Okay, subsets. And this is the basic structure of monomorphisms in this category set to the power of C. And it's very cool because on one hand, we can have all this kind of abstract theory of monomorphisms and how they relate to logic and, sub-object classifiers and all the rest of it. We can have all this sort of abstract theory of that stuff because set to the power of C is a topos. But on the other hand, we can actually get at all of this stuff concretely. We can really talk about all this stuff in terms of set theory and these kind of substructures of our objects. We can talk about that in concrete terms as well. So it's nice that we have these kind of connections. And so there's some results I want to talk about to do with monomorphisms. So firstly, just a recap. What is a monomorphism in general? Well, it's just an arrow. So a monomorphism M from X to A is an arrow M from X to A. And to be a monomorphism, okay, so the first question is, what is a monomorphism? So a monomorphism M from X to A is an arrow M from X to A with the property that whenever we have a pair of arrows X and Y from some object H to X, the source of our arrow M, we have the property that if M after X equals M after Y, then X equals Y. Okay, and such a monomorphism M that's going into object A, we can consider that to be a sub-object of A. So that's just sort of terminology, really. When we say we have a sub-object M of A, we just mean that M's a monomorphism going into A. And sometimes I call monomorphisms monics. Okay, it's a bit shorter. So here we have a picture of a monomorphism into this object A. This is an object in our category of functions. This is a bouquet, essentially. And, we can think of X really as a sort of sub-bouquet. And here, this monomorphism M, it's kind of like what they call an inclusion function. Okay, so an inclusion function, if you have a set 1, 2, 3, and then you pick a subset of that, let's say 1, 2, well then there's a sort of inclusion function which basically it maps 1 to 1 and it maps 2 to 2. Okay, so it doesn't alter the value of anything it maps, it just considers the things post mapping to be present in a potentially larger set. Okay, so that's an inclusion function. And you can see that basically we can represent this monomorphism here so that it's different components, as in the way it works on vertices and the way it works on loops, are inclusion functions. And it turns out that every monomorphism. So, okay, There are monomorphisms that are not like this. You know, we could also just, if we relabel this to be a Q or something, that's fine too. As a mapping, it's just now it's sending Q to A, but it's still basically a monomorphism. In fact, it's kind of equivalent. And it turns out that every monomorphism is equivalent to one of these kind of inclusion function based monomorphisms in this category set to the power of C. So the structure is really quite straightforward, but I want to rigorously establish this because monomorphisms are sort of important for talking about topos theory and so on. And so I'm going to run through some theoretical results, and I'll put the proofs attached in the description to this video. I'll call them the videos monic proof. Okay, so you can see those in the attached. Right, so okay, first result then I call the monohom lemma. So the basic idea is that this is the defining feature of a monomorphism. Okay, basically that for any sort of parallel arrows going into the source of M, we have that if M after X equals M after Y, then X equals Y. Okay, but you know, in order to test if a particular monomorphism, if a particular arrow M is a monomorphism according to this definition, we'd have to test it for every pair of parallel arrows. Well, there's a lot of arrows going into objects in most categories that we're interested in, so it's a bit unfeasible to sort of test all of them. And it turns out that for us, it's enough just to test the arrows coming out of a Hom functor. Okay, so the basic idea is that if you think about, for example, the category of sets, what's a monomorphism in the category of sets? Well, it's basically just a one-to-one function, okay, a function that doesn't collapse elements. But what is that? Well, basically, it's sort of, you think of it as being defined by the feature that if we have any couple of functions from a singleton set, say X and Y, like so. I'm going to draw that other one in another color because these are two different functions. Okay, so we've got X coming in from a singleton set and Y coming in from a singleton set. Then we have the if M after X equals M after Y, then X equals Y. In other words, when you do a monomorphism in the category of sets on a particular element in a set, in other words, if you have a monomorphism M in the category of sets and you apply that function to two elements, X and Y, then you only get the same result if X was equal to Y in the first place. Okay, so basically what I'm saying is that in the category of sets, it's enough to know that your mapping is working the same on elements, that it composes the same with these arrows coming in from the terminal object. And basically it's a similar idea in the category of in the category set to the power of C. It's just that in this case we're not just dealing with elements of sets, we're dealing with, but so it's basically the same kind of story in set to the power of C. It's just that in set to the power of C, our objects are not just sets, they're these kind of structured sets that, you know, they involve like a set of E-type figures, a set of V-type figures, and so on. And it turns out that the monomorphisms are precisely the functions that are sort of one-to-one on the E-type elements and the V-type elements, and it turns out that in this category set to the power of c, the monomorphisms are just the arrows in set to the power of c, which if you look at their components, because you know these arrows in set to the power of c are actually natural transformations and they have different components, and as long as each of those components is a one-to-one function, so in other words, as long as your mapping is one-to-one on E-type elements and one-to-one on V-type elements and so on, then it will correspond to a monomorphism. And vice versa. So that's the result kind of formalized by this first result, which I call the mono-Hom lemma. And I mean, the basic idea here is it's basically what I just said. So, for example, okay, in this category of functions, this is a monomorphism, and you see it basically involves a one-to-one function from the loops of x to the loops of a, and a one-to-one function from the vertices of x to the vertices of a. So it's one-to-one on the E-type figures, the loops, and one-to-one on the V-type figures, the vertices. And all monomorphisms in set to the power of c have this kind of form. Now this is formalized by this mono-Hom lemma, but here I talk, instead of talking about like E-type elements and V-type elements and so on, I represent these as arrows from the Hom functor. So I'm sort of using the Yoneeda correspondence here. But you know, the basic idea is just that, okay, so let me now tell you the mono-Hom lemma sort of formally. An arrow M from an object X to an object A in set to the power of c is a monomorphism if and only if for every object E of c we have that for any pair of parallel arrows zeta and zeta dash from Hom E comma blank to X, so these are really corresponding to E-type figures of X, or if you like, corresponding to kind of members of X of E anyway. The point is that for any pair of these parallel arrows, zeta and zeta dash, we have that m after zeta equals m after zeta dash implies zeta equals zeta dash. Okay, so this is the basic result. And for example, think about this case. We have this So, for example, we have the kind of solid solid arrows drawn in this sort of representation of this arrow M from X to A. These solid arrows obviously are signifying that this kind of mapping here is like a one-to-one mapping on the vertices. And a way we could say this is that, you know, we have our single vertex here, which is Hom. Which is Hom V comma blank, and it has the feature that if we have a pair of parallel arrows coming from Hom V comma blank into X, let's say X and Y, then we're only going to have M after X is equal to M after Y when M is equal to then we're only going to have M after X equals, then if we have M after X equals M after Y, then it must be the case that X equals Y. Okay, so this is the kind of idea. In fact, we should probably call these arrows zeta and zeta dash, then we're corresponding to the language used here in Mono Harm Lemma. Anyway, like I say, you can find the proofs of this, these results I'm sort of discussing now. You can find all the proofs in this attached video in the description. Anyway, another really important idea, really important when it comes to talking about monomorphisms, is this idea of when an arrow H is in a monic M. Okay, so we have this subobject M of A, and we have an arrow H into A, and we say that H is in M if and only if there exists an arrow K such that H is equal to M after K. All right. Now it turns out that we can really get a lot of understanding about what this concept means in our case, and it's basically saying, for us, when we write H is in M, we're sort of essentially saying that we can think of M here as like a sort of structured load of subsets of A, and so we can think of M here as a sort of structured load of subsets of A, and we can basically, when we write H is in M, we're essentially saying that all of the stuff in H gets mapped to stuff which are belonging to these kind of subsets. So think about, for example, if I have some mapping into A from some bouquet H, and you see I'm essentially selecting a kind of subset here with this kind of substructure. So you can see here I'm essentially selecting kind of substructure of A with this monic M, and if H sends everything just into this substructure, then we'd say H is in M. Okay, so that's kind of fuzzy way of describing it, but I'll get on to how we can say this concretely with some of these other results. But the important thing is the kind of formal definition, like here, of when H is in M, because this sort of definition here applies for any kind of monomorphism M in any category. Okay. Anyway, here's another important concept, and that's when one monic M is contained in a monic M. So suppose we have two subobjects M and N of this object A. Now we write M is contained in N if and only if we have that M is in N. So in other words, when there exists some arrow K such that N after K equals M, but it turns out that there's an equivalent way to say that M is contained in N, which is something I proved in a previous video. So this is again holding for any category. And it turns out that saying M is contained in N is equivalent to saying that for any arrow H, which goes into A, we have that H is in M implies H is in N. Okay, so it turns out that this here is a sort of equivalent way to say that M is contained in N. And this is pretty cool because if you think about it, like in terms of sets, like think about what's going on for sets. Well, we say that one subset is so we say that one set is contained in another set when every element of the first set is an element of the second set. Mm-hmm. And you see that here we really have a sort of generalization of this notion, because we're essentially saying that a sub-object M is contained in a sub-object N when every arrow that's in M is also an arrow that's in N. Now, another thing which is going to come up later, we say that two sub-objects are equivalent, written with this triple equal sign, so M is equivalent to N, and this happens if and only if M is contained in N and N is contained in M. And if you look at this purple thing I've circled in red, you can see that this condition here essentially means that any arrow with the same kind of target as M is going to be in M if and only if it's in N, precisely when M and N are equivalent sub-objects. So just like two subsets are equal when they have precisely the same elements, so just like two subsets are equal when they have precisely the same elements, we have that two sub-objects are equivalent when there's precisely the same arrows in each of them. So this is all general stuff again. This is not specific to the category set to the power of C. And let's talk about some more. But anyway, now let me define something important. Well, I think I've already talked about this really, but suppose we have a subset Y of a set Z. So this is in the category of sets, of course. So now we're talking about set theory. And when we have that Y is a subset of Z, we can think of Y as an object in our category, of course, because the objects are sets in the category. Okay, so now let me talk about something important for Okay, so let me now talk about an important kind of idea for us making this connection for a set to the power of C. So this is basically the idea of an inclusion function. So again, suppose we have this set 1, 2, 3, and then we have this subset 1, 2 here. So if we call this subset Y and this set Z, of course, we can think of these as being each set, and then we have an inclusion function I here, and the idea is that an inclusion function is just sending every element in Y to itself, but considering it so the idea of this inclusion function is just that it's sending every element of Y to itself, but considering it as part of this larger kind of set Z. Okay, so if Y is a subset of Z, then the inclusion function from Y to Z is just going to be such that for every element little y of capital Y, we have that I sends little y to itself, but in Z. Okay, now here's an important result, which basically just kind of proposes that there are these kind of special monomorphisms in set to the power of C that look kind of like this, where like each component of M, when considered as a monomorphism, look like these inclusion functions. Okay, so more precisely then, because I mean to set this up properly, we need to sort of think, well, we've got this sort of family of subsets. So in this case, for example, we've got a subset of the vertices and a subset of the loops. And we can't just pick any old subsets. They have to basically have the property that when we take these kind of subsets of E-type elements and V-type elements and so on together, they form a proper kind of object in their own right. And what this basically boils down to is that they're sort of closed under S actions. Okay, so if we have an arrow S from E to V in our category C, then if we do like A of S on something in one of our subsets, then we're going to get something in another one of our chosen subsets. So for example, we wouldn't be allowed to just like pick a single loop and not have the vertex of that loop present in our subset, because whenever we have a loop in A, we do an S action on it, we get a vertex of A, and that's sort of necessary. We need that necessary structure for in order to have a properly defined object X. We have to have the property that every loop has a vertex. In other words, doing the S action on a loop gives a vertex. So our sort of collection of subsets, which is we can think of as really defining this subobject X here, has to be sort of closed under S actions. So this is formalized by this next result. And I call this inclusion lemma 1. So what it basically says is that if we have an object A of set to the power of C, let's suppose that for every object E of C, we pick some subobject A. So here's the inclusion lemma 1 then that formalizes this notion. So the idea is that suppose we have an object A of set to the power of C. We want to make a subobject of it. So for this set A of E, let's pick a subset of it, A subscript E. And we'll do this for every object E of our category C. So we're essentially getting a subset of the E-type elements of A and a subset for V-type elements of A and so on. Now, is that collection of subsets going to allow us to form a kind of sub-object of A? Well, not necessarily. We need it to satisfy this extra condition that this kind of collection of subsets is closed under S actions. Okay, so in particular, I mean that we know we have this function A of S, which sends E-type elements of A to V-type elements of A for every arrow S from E to V in our category C. But we want this kind of function here to send elements of our chosen subset A of E to elements of our chosen subset A of V for every arrow S from E to V in our category C. Okay, so basically what I'm saying is that here, let's just pretend this is our set A of E, and here's our set A of V, and we pick a sort of subset A subscript E, and we pick another subset A subscript V, but we're assuming then for any S action, so for any arrow S from E to V, we have that this kind of function AS here is always going to map elements in A subscript E to elements in A subscript V. Okay, so this means our sort of chosen collection of subsets is kind of closed under S actions, if you like. So if we have some elements of A of E, then A of S sends that to some element of A subscript V, and so on. So what I'm saying is that if we have some elements of A subscript E, then we have to be sure that A of S sends that to some element A subscript V. So here's the kind of formal statement of this idea then. For every object E of category C, we select some subset A subscript E of A of E So here's the kind of formal idea then. For every object A of set to the power of C, suppose we... So here's the idea then. Given an object A of set to the power of C, we suppose we have this collection of subsets. So for every object E in the category of C, we have some subset A of E of... So here's the formal idea then. Suppose we have an object A of set to the power of C, and then for every object E of the category C, we select a subset A subscript E of A of E. And we suppose that this collection of subsets, this is the important bit, we suppose that this collection of subsets is kind of closed under S actions. So more precisely, for every arrow S from an object E to an object V in our category C, of course we have this function A of S, which is a function from A of E to A of V. But we suppose that this is sort of always going to send things in A subscript E to things in A subscript V. So more formally, for every such arrow S, we have that A of S is always going to send elements of A subscript E to A subscript V. So this is what we want. And when we have this kind of stuff, we can always build a kind of functor. And so this is what we want. And when we have this kind of stuff, we can always build a kind of corresponding, in what I call an inclusion monic. So the idea is then that we can define another object. This is the claim. The claim is then that we can define another object, X, of set to the power of C. And we can set X to have the E-type elements of X and we can have this X so that the E-type elements of X just consists of A subscript E, and so on. So that's basically how we can sort of form this kind of sub-object, which is kind of injected into A by all these by a kind of mapping where every component looks like an inclusion function. So I'm basically trying to say, well, we have this collection of subsets, a subset A subscript E of A of E, and a subset A subscript V of A of V, and so on. And then we can form an object X such that the kind of E-type elements of X equal, such that the kind of set of E-type elements of X equals A subscript E, and so on. And so how do we form this object X? And so how do we form this subobject X? Well, I've just told you how we can get A of E and A of V and so on. We just set them equal to this A subscript E and so on. But what about the S actions under X? Well, all we do for the S actions is we just let X of S be the kind of restriction of A of S to A of E. Okay, so the idea is that we can form this kind of collection of subsets like subset A subscript E, like a subset A subscript E of A of E, and so on. And then if we just look at the kind of restriction of our kind of action mapping A of S, but restrict it to these subsets, then we can think of that result as being a kind of action of X. Okay, so basically the action of, so basically doing an S action in X looks just like doing the same S action in A when we look at it as how it corresponds to these kind of functions that work on particular elements. So more formally then, for every object A of set to the power of C, we let A subscript E be the subset of A of E. So more formally then, let's suppose that for every object A of set to the power of C, we have that A subscript E is just a subset of A of E. But these subsets, let's suppose that they have the property that this kind of S action function here, A of S, suppose it always sends elements of A subscript E to elements of A subscript V for every kind of arrow S from E to V in our category C. Well, in that case, we have that we can form this kind of object X of set to the power of C. And it has the properties that X of E is equal to this subset, A subscript E, and so on. This holds for every object E of the category C. And also, because I mean, this tells you like what the E-type figures of X is, and what. So I mean, this tells you what the E-type elements of X are, and what the V-type elements of X are, and so on. But the other thing you need to know is how does the kind of S action work? But the other thing you need to know is like how does the S action work on stuff that's in X? And basically the idea is that the S action, doing the S action in X looks just like doing the S action in A. Okay, so more precisely, we define X of S to be the kind of restriction of A of S to this kind of subset A subscript E. So it's just like this kind of situation that I've drawn. We have these kind of subsets, we have these kind of subsets, A subscript T and A subscript V. And we're saying that this function A of S always sends elements in A subscript T to elements of A subscript V. So basically then what we do is we form this object X so that we have that X of E is basically equal to A subscript E, and A of V is basically equal to A subscript V. And then the S action X of S is just a kind of function from X of E to X of V. And this function basically works just like the function A of S works. It's working on a subset. It's mapping something into a subset. So in this case, the claim is that X is actually going to be a proper object of set to the power of C. But moreover, also, there's going to be a kind of natural transformation I from X to A, and then the kind of ETH components of that natural transformation for any object E of the category C is just going to be an inclusion function, okay? And in this case, with all this sort of kind of complicated setup, the final claim then is that this kind of mapping I from X to A, which has each of its components as an inclusion function, kind of including this subset A of E, kind of including this subset X of E into A of E. Well, the claim is that this kind of mapping I here is always going to be a monomorphism. So for this reason, we call such a kind of mapping I an inclusion monic, okay? Because essentially each of its kind of components is just going to look like an inclusion function. So this is the basic claim then of inclusion lemma 1. In a nutshell, what it basically says is that if you pick a load of subsets of A, which are closed under any S action, then you can think of that collection of subsets as sort of forming another object X of set to the power of C, and then you can think of the kind of and then if you set things up like this, you are going to have that X as a proper object set to the power of C, and you're also going to have that this kind of map I, which has each of its components looking like an inclusion function, we have that arrow I is itself going to be a monomorphism of set to the power of C. And this is really just the kind of thing we've pictured up here. Okay, basically, if you select a load of subsets of A and they're closed under S actions, then you're going to have this kind of sort of inclusion map, if you like, or a sort of map that has each of its components equal to an inclusion function. And this itself is going to be a monomorphism. So that's inclusion lemma 1. The other thing I wanted to establish is this thing, inclusion lemma 2. And that basically says that this kind of inclusion monic, which I just described, and the idea of inclusion function, and the idea of inclusion map 2 is basically that any monomorphism in set to the power of C is essentially equivalent to a sort of inclusion monic as I've just described. Okay. So, I mean, yeah, there's going to be usually lots of equivalent sub-objects, which basically are kind of like injecting structured sets with maybe differently labeled elements into A. But each of those kind of monomorphisms into A, each of those kind of sub-objects of A, essentially has this kind of form I've just described, or at least it's equivalent to something with that form. So we can always find this kind of monomorphism, which is an inclusion monic, which has each of its components equal to inclusion functions, essentially. And the inclusion lemma 2, and the inclusion lemma 2 especially says, and then the inclusion lemma 2 essentially says that every monomorphism is equivalent to something of this form in set to the power of C. So it's a very powerful result, really. So, for example, if you're looking at this case here, M is obviously a monomorphism from X to A. But in this case, M is actually more than that. It's a kind of inclusion monic, according to what I've just described. But it could be the case we could consider a different type of scenario where, you know, things are not so straightforward. Maybe this loop's called something different. Maybe it's called Q. Okay. And in this kind of situation, we have a monomorphism. We have a sub-object of A, but it's not an inclusion monic because each of its components is not just a kind of because each of these inclusion functions is just kind of including the thing in it. Okay. So when we have something like this, we can essentially call, so when we have a setup like this, where we have this kind of, so when we have this setup, so that's the essential content of lemma 2. It essentially says that any sub-object in set to the power of C is essentially equivalent to one of these kind of inclusion monics. So yeah, the components of M, so yeah, the components of a kind of general monomorphism M might not always be inclusion functions. For example, we might have this case here where we're sending a loop Q to A. For example, we might have a situation like this here where we're sending a loop Q to A instead of just sending A to A. So in this case, the way that this map M works on loops is not just going to be an inclusion function, but it is going to be a one-to-one function. And we might as well have called Q A, really, since in category theory, we don't really care about how the elements in these sets are labeled. But, you know, we're starting to care a bit more now because we're trying to establish this result. Because, you know, the essential definitions of category theory, like the ideas of monomorphism, don't really depend on how these elements are labeled. But the important idea here is that given any monomorphism M, we can always sort of find something equivalent to it where the way that things are labeled in the kind of source set are basically the same way they're labeled in the target set. So we can think of that kind of monomorphism as sort of inclusion monic, where all the kind of components of that arrow in set to the power of C look like inclusion functions. So this is the idea of the inclusion lemma, or at least inclusion lemma. So this is the idea of these inclusion lemmas. Inclusion lemma 1 says we can always kind of, inclusion lemma 1 says how we can build up these kind of inclusion monics by selecting the kind of subsets of the E-type figures of A for every E kind of specially, so that they're closed under S actions. And then lemma 2 says that, and then we form this kind of arrow I from X to A in set to the power of C, but it just has each of its components equal to this kind of inclusion function, which is essentially kind of including this sort of subset into A. But of course, there can be other kinds of monomorphisms, ones that maybe alter the name of elements, like this one I've pictured here, which is sending Q to A and so on. But the point, as given by inclusion lemma 2, is that every monomorphism in set to the power of C is equivalent to one of these kind of inclusion monics. It has the same members, and we can essentially think about all the monomorphisms as corresponding to these kind of inclusion monics, if we like. So, okay, that's basically it. There's just one more important kind of theoretical result, which I want to state, which I call the membership lemma. Now, the membership lemma basically says that if we want to see it, so the membership lemma basically says that an arrow H is going to be in a subobject M in set to the power of C. So precisely when each kind of E figure, precisely when H kind of maps every E figure theta of the source, precisely when H kind of maps every E figure theta to something which is kind of contained in this sort of subobject. So more. So then the sort of final result I want to state is this so-called membership lemma. So formally what this says is that given a subobject M of A, what we're going to have is that M is going to be, so what this membership lemma says is that given a subobject M of A, and also an object little h into A, what we're going to have is we're going to have that H is in M if and only if for every arrow, for if and only if for every element theta of H of E for any object E of the category C, we have that H after the map corresponding to theta is going to be in M. Okay, so like you might want to watch the proofs of this video to sort of see what this result really means. But essentially what it's saying is that if we have any kind of monomorphism M in our category set to the power of C, we can always find one of these kind of inclusion monics, which it's equivalent to. And then what this really means is that the thing which defines this subobject M, really, the important thing that defines it is which kind of E-type elements it has for every E, or if you like, which arrows from the Hom functor are in it. And essentially this membership lemma goes further. It says that so essentially what this membership lemma is saying is that if we're given this subobject M of A, I mean, we can really think of this as an inclusion monic, kind of by this correspondence that I've been talking about. We can think of this really as just kind of including substructure of A into A. Okay, and basically what this result's saying is that an arrow H is going to be in M precisely when all of the values of H are taken within this kind of substructure, which is sort of swept out by this subobject M. And a more sort of precise way to say that is that H is going to send every E-type element of H to a sort of E-type element of this kind of substructure defined by M. And the sort of way to say this with the Yoneda lemma is to say that given any E-type element theta of H, if we find that H is going to send that E-type element to something in M, but we can say this with the kind of arrow-based language, and so we're essentially saying that if we find the kind of arrow from the Hom functor that corresponds to theta, in other words, theta under arrow, then composing H with that theta under arrow gives us something that's in this subobject M in the kind of formal sense that we're talking about. But so just to sort of compare and contrast this kind of result, like I'll show you something more general than this and something less general than it. So a more general result is that we're going to have in a general category. So this, these lemmas, all of these lemmas and theorems I've just talked about are all, working in the category set to the power of C for a general C. But if we're working in a general category, then we have this result that we're going to have that H is in M if and only if for every sort of arrow alpha which goes into the source of M, we're going to have that H after alpha is in M. Now, if we're working in the category of sets, we have an even more specific result, which is saying that for any arrow alpha just from the terminal object into the source of our arrow little h, we have that H after alpha is in M, which is essentially saying that in this case of a category of sets, it's saying that this function H is taking all its values in this kind of subset M, in this kind of subobject M. Okay. But anyway, here's the inclusion lemma, and we prove it in the attached videos.